Welcome to Math 104, Section 7.6, Solving Equations with Radicals. Please start with a warm-up. All right, so we've got square root of x. We're going to square it. When written like this, you have the effect of canceling each other out, and we've got an x. Now we have to be careful with this one, though, because this one, we could plug a negative number in there, and as we saw in Section 7.1, 7.2, that, when we square it and then take the square root, would turn into a positive number. So this one is where we have to have the absolute value there. All right, this one is like the first. We get x plus 5. And then this one, another absolute value, x minus 3. And in a moment, I'm going to discuss the difference between those two. And we're actually going to be using this version and this version today, so we won't need to worry about the absolute value. So we're going to be solving equations with radicals in them. And the strategy is going to be to eliminate the radical. And so we're going to be using techniques like this, and we're going to be taking each side of the equation to a power to do it. So we're going to be using this property, raising each side of an equation to a power. So if one side equals the other, once we raise them to the power, they're still equal to each other. And so that's an important property we'll be using. But that property has a downside. It can introduce extraneous solutions, extra solutions that weren't a solution to the original equation. So let's take a look at this example. Let's say we let x equals 2. So we already have our solution, we're already solved. But let's use this property and square both sides. So if x equals 2 and we square both sides, we know that these two sides are equal to each other based on that property. So we have x squared equals 4. Now if we solve that equation, we can get two solutions. 2 is a solution to this equation, but negative 2 is also a solution to the equation, because when we square negative 2, the negative goes away and it becomes positive 4. So this is a solution to the original equation, but this extra solution here is a solution to our new equation, but it's not a solution to the original equation. And the reason we get extra solutions is we've gone from a first order equation where the highest exponent is 1, and those types of equations only have one solution. But then we've gone to a second order equation. Right? This is a quadratic equation. And quadratic equations have generally two solutions. So that's why we get the extra solution. So every time we solve one of these using this property, we're going to need to check every solution to make sure it's a solution to the original equation as well. So let's see how that works. All right, we are going to go through the procedure. First step, isolate the radical. Make sure one radical term is alone on one side of the equation. And we want it to be alone because if we have something added to it, that means we're going to have to FOIL. So we don't want to do that. Get it by itself so that when we square both sides, the radical just goes away. Now, why is this different than this one? The difference is the radical. Let's say we plug in a value here so that we get a negative number underneath radical. We could plug in negative 1 here. That would give us negative 3 minus 5 or negative 8. But the square root of a negative number isn't a real number. So that means we can just forget about plugging any number in for x that's going to give us a negative here. And that eliminates this problem here, where you get a negative number, squared it, turns positive, take the square root, and you get a positive value, which doesn't match the negative value we had on there. That's why we need the absolute values here. But that cannot arise here because we cannot have a negative value underneath the radical. So, nice thing about these is we don't need to worry about the absolute value. We're just going to square both sides, and the exponent and the radical cancel each other out. So we just get 3x minus 5 on this side. And on the other side, 5 squared is 25. Now you've got a regular linear equation to solve. Plus 5, 3x equals 30, divided by 3, and x equals 10. All right, so let's check this value of the original equation. I'm going to take 10, plug it in here. 3 times 10 is 30, and minus 5 is 25. Square root of 25 is 5. So that works. Now, generally, we're not going to get extraneous solutions if, when we square it, we get a linear equation. And that's what happens if we have just a radical here, square it, and they cancel each other out. But we will get extraneous solutions in other situations. All right, go ahead and solve this, and just for practice, make sure you check. All right, both sides squaring. That gives us 4x minus 8, if we cancel here, equals 16. I'll add 8 to each side. 4x equals 24, divided by 4, and x equals 6. Let's make sure it works. Take 6, plug it in here. 4 times 6 is 24, minus 8 is 16, square root of 16 is 4. So that works. Now over here, some of you are going to look at this and see a problem right away. But let's go ahead and solve it and see what happens. So we use this technique, square both sides. It gives us 5x minus 3 equals negative 2 squared is positive 4. All right, plus 3, 5x equals 7, divided by 5, and x equals 7 fifths. All right, let's plug 7 fifths in here. 5 times 7 fifths, the 5s are going to cancel, leaving just 7 here. 7 minus 3 is 4. Square root of 4 is 2. Uh-oh. Negative 2. That doesn't work. It's not a real solution. And it's the only one we have. So that means there's no solution to this one. Why? Well, the original equation was this. Square root of something equals a negative number. Well, square roots can't be negative. Your turn, number 2. So squaring both sides, 4x plus 3 equals 1. Subtract 3, subtract 3. That gives us 4x equals negative 2, divided by 4, and x equals negative 1/2. So I'm going to take negative 1/2, plug it in here. Negative 1/2 times 4 is negative 2, plus 3 is positive 1. Square root of positive 1 is 1, so it does not equal here. That's not a solution. Empty set. All right, so all the ones we've seen so far, the radical has started off by itself on one side of the equation, but that's not always the case. So if it's not, we're going to start by isolating the radical. Get it all by itself on one side of the equation. So this one's not by itself, it's got this -5 next to it, so we're going to add 5 to both sides of the equation. So if we don't, we're going to have to put parentheses around this squared, and then we're foiling, and then it's a big mess. So that gives us the square root of 6x plus 10 equals 8. And now we can square both sides since we have the radical by itself. So that gives us 6x plus 10 equals 64. Subtract 10 from each side. 6x equals 54 divided by 6, and x equals 9. All right, let's see what we got here. 9 times 6 is 54, plus 10 is 64. Square root of 64 is 8, so that works. Your turn, number 3. All right, so we're going to get the radical by itself, add 1 to each side. That gives us square root of 2x minus 1 equals 3. And at that point, we can square both sides. So we got 2x minus 1 equals 9. We're going to solve this now, add 1 to both sides. We get 2x equals 10. Divide each side by 2, and we get x equals, whoops, x equals 5. All right, let's check this. 2 times 5 is 10, minus 1 is 9, square root of 9 is 3. So x equals 5 works. All right, next one, we're going to put a few more variables in there. Yeah, it's become a little bit more complex. So we'll have to either FOIL the right side or remember your perfect square trinomial formula. All right, we have the radical isolated, so we'll square both sides. All right, they cancel here, so we get 5 minus x equals x squared plus 2x plus 1 from the perfect square trinomial formula. All right, now I want to get everything to one side so we can solve this thing, or we're going to use the zero factor property. So I'm going to subtract 5 from both sides and add x. So then we get 0 equals x squared plus 3x minus 4. Now we can factor. And that factors into x plus 4, x minus 1. Now we've got two equations to solve here. X plus 4 equals 0, and x minus 1 equals 0. So x equals negative 4, and x equals 1. All right, now we have two solutions. And one of these is definitely going to be extraneous. So let's take negative 4, plug it in here. So that is 5 minus negative 4, which is the same as 5 plus 4, which is 9. Square root of 9 is 3. Over here, negative 4 plus 1 is negative 3. So that does not work. That is extraneous. Now let's try 1 just to make sure. 5 minus 1 is 4. Square root of 4 is 2. On this side, 1 plus 1 is 2. So this one does work. So x equals 1 is the real solution. Your turn, number 4. There, we have the radical isolated, so we'll square both sides. We got a cancellation here, so that gives us 3 minus x equals x plus 3 squared. So that's x squared plus 6x plus 9. And now let's get everything to the right. So I'm going to add x to both sides and subtract 3 from both sides. So 0 equals x squared plus 7x plus 6. And this will factor into x plus 6 times x plus 1. So when we solve both these individually, we get x equals -6 and x equals -1. So let's check those. We're going to take -6 and plug it in here. 3 minus -6 is 3 plus 6. So that's 9. Square root of 9 is 3. Over here, -6 plus 3 is -3. So that does not work. Now let's try -1. 3 minus -1 is 3 plus 1. So that is 4. Square root of 4 is 2. -1 plus 3 is 2. So this one does work. The real solution is x equals -1. So we have the radical isolated on this one. So we can go right to squaring both sides. So we get 6x plus 7 on the left. And x plus 2 squared gives us x squared plus 4x plus 4. All right, let's get everything to the left. Minus 6x on both sides. Minus 7. So we get x squared minus 2x minus 3. Factor in, we get x minus 3 times x plus 1. Setting both of these equal to 0. We get x equals 3 and x equals -1. Now let's try these out. Take 3, plug it in here. 6 times 3 is 18, plus 7 is 25. Take the square root of 25, we get 5. 3 plus 2 is 5, so that one works. -1. 6 times -1 is -6, plus 7 is 1. Square root of 1 is 1. -1 plus 2 is -1, so they both work. So this is one of those rare cases where we're starting off with something that initially appears to be linear, it's not really, and transform it to a quadratic, and both of the answers work. So it's pretty rare that it happens, but it does happen. And that brings us to your turn, number 5. All right, we're going to square both sides. That gives us 4x plus 13 equals, we're going to square this to get x squared plus 8x plus 16. We get everything to the right, so let's subtract 4x from both sides and 13 from both sides. And we get 0 equals x squared plus 4x plus 3. And that factors into x plus 3 times x plus 1. Setting both equal to 0, solving individually, we get x equals -3 and x equals -1. Let's see if these are going to work. Plug in -3 here. Gives us -12 plus 13 is 1. Square root of 1 is 1. Over here, -3 plus 4 is 1. So that works. -1 up here gives us -4 plus 13 is 9. Square root of 9 is 3. -1 plus 4 is 3. Both of those check, so they are both solutions. So up to now we've been looking at all square roots. Now we're going to look at some radicals with higher indices. Fourth root of 5x plus 6 minus 3 equals 0. So just like with the others, first thing we're going to do is isolate the radical. And that gives us the fourth root of 5x plus 6 equals 3. Now we're going to raise each side of the equation to a power that equals the index. So that'll be the fourth power. So we get 5x plus 6 equals 3 to the fourth, which is 81. Solving. 5x equals 75. And x equals 15. Now let's check. Plug in 15 here. 15 times 5 is 75, plus 6 is 81, fourth root of 81 is 3. So that works. Your turn, number 6. All right, we're going to start by isolating the radical. Subtract 7 from each side. So we get the third root of 2x plus 4 equals negative 2. Now we saw one earlier where a root equaled to negative 2 and we got no solution. But this is the third root, so we can get negative numbers, so that's fine. Now we're going to raise both sides to a power equal to the index, so that is the third power. All right, 2x plus 4 equals negative 2 to the third is negative 8. Subtract 4 from each side, and we get 2x equals negative 12, divided by 2, and we get x equals negative 6. Let's make sure this works. We'll take negative 6, plug it in here. That's negative 12. Negative 12 plus 4 is negative 8. Third root of negative 8 is negative 2. Negative 2 plus 7 is 5. So that works. All right, next example, we've got a radical on both sides. Now, fortunately, the only thing we have is a radical on both sides. This is a little more straightforward than what we're going to see coming up. So you got the third root of 2x plus 7 equals the third root of 3x minus 2. All right, we want to raise to a power equal to the index. So that's the third power. That'll cancel out those radicals, and we get 2x plus 7 equals 3x minus 2. And we just got a regular old linear equation to solve. So I'm going to subtract 2x from both sides, and we got all the x's to the right. So I'm going to move the numbers to the left, and we get 9 equals x. All right, let's make sure this works. 2 times 9 is 18, plus 7 is 25. So we have the third root of 25. Over here, we got 9 times 3 is 27, minus 2 is 25. Third root of 25. So that works. We don't have to evaluate these to get a whole number. We can leave them as radicals, and if they equal each other, it checks. Next up, we have your term number 7. All right, we've got two radicals with the same index 3. So that means we're going to raise both sides of the equation to the third power. I'll get rid of the radicals, and we have x squared plus 2x plus 8 equals x squared plus 3x plus 12. All right, we've got an x squared on both sides. We can subtract those out. I'll get rid of those. And now we want to get all the x's to the right. So I'm going to subtract 2x here, 2x here. Get the numbers to the left, minus 12, minus 12. All right, 8 minus 12 is negative 4. Only thing left over here is an x. So x equals negative 4. All right, plugging in here, it gives us 16 minus 8 plus 8 is 16. So we get the third root of 16 over here. Over here, we got 16 minus 12 plus 12 is 16. So third root of 16 on both sides. So that checks, and x is negative 4. All right, now we're going to see a more advanced situation. This is an equation with two radicals, but not like this where they're just set equal to each other. A little different here. So we're going to do the square root of 2x minus 5 plus square root of x plus 1 equals 3. Now, we want to get one of the radicals by itself. So I'm going to subtract 1 and move it over to the other side. All right, so I'm going to subtract the square root of x minus 1, or plus 1, from each side. That gives us the square root of 2x minus 5 equals 3 minus the square root of x plus 1. So that's the best we can do before we start squaring. So this is the situation we were trying to avoid before, but this time we cannot avoid it. So we're going to have to either FOIL here, or just remember your perfect square trinomial formula. So over here, we're going to get cancellation, so we get 2x minus 5. And over here, we get first term squared, so that's 9. Now, 2 times a times b, so that's minus 6 square roots of x plus 1, just by the perfect square trinomial formula. And the last piece will be plus the square root of x plus 1 squared. And that cancels to just give us x plus 1 there. All right, now we are going to get that radical by itself and then start the process all over again. So I'm going to move everything to the left-hand side. Minus x, minus 1, minus 9. Now we're subtracting a total of 10 on this side, so I'm going to subtract 10 over here and an x over here. All right, all this stuff goes away, leaving just negative 6 square root x plus 1. And over here we get x minus 15. Now we're down to a radical on this side, and yeah, it has a coefficient, so it's not completely by itself, but when we square it, that's no big deal. What we want to avoid is something added to it, so we have to FOIL. But something multiplied, that's fine. All right, let's square both sides. All right, I'll have to evaluate this. So using the perfect square trinomial formula, that gives us x squared minus 2 times x times negative 15, which is negative 30x, and then 15 squared plus 25. And then on this side, we're going to do negative 6 squared, which is positive 36, times square root of x plus 1 squared, which is x plus 1, in parentheses. Now we're going to have to distribute over here. (36x plus 36). Now we get everything to the left. I think that's right. I'm going to check that one. Minus 66 plus 180. Yeah, that's right. Okay, so that's the thing we have to factor in. That's going to be fun. So we got 63 and 3. So you get x minus 63 and x minus 3. So there's factorization. We'll solve these each individually. X minus 63 equals 0 and x minus 3 equals 0. So x equals 63 and x equals 3. All right, let's check now. Going back to the original equation. 2 times 63, that's 126, minus 5 is 121. Square root of 121 is 11. So we got 11 here. Over here, we'll do 63 plus 1 is 64. Square root of 64 is 8. So that gives us 11 plus 8, which is 19, does not equal 3. So 63 is extraneous, not a real solution. All right, let's try 3. 2 times 3 is 6, minus 5 is 1, square root of 1 is 1. Over here, 3 plus 1 is 4, square root of 4 is 2, 1 plus 2 is 3. So this one works. X equals 3 is the real solution. All right, so pretty long one there. Give that a try with your term number 8. All right, so let's go right to squaring. Got one of them isolated, so that's as good as we're going to get. All right, over here. All right, we'll square this part. That gives us 2x plus 7. Now for the middle term, we have 2 times the radical times 1. So that's plus 2. Square root of 2x plus 7. And then plus 1 squared, so we get 1. Now if you have trouble using the perfect square trinomial formula like that, just go ahead and, what I recommend do is writing out 2 of these next to each other and then foiling. It's a lot easier to foil if you write them 2 binomials next to each other than with one of them squared. Over on this side, all right, we'll cancel the radical and the power, we get x plus 15. All right, now let's get this thing by itself. So I'm going to subtract 7 and subtract 1 here. That means I have to subtract 8 on this side. And we'll subtract 2x. All right, that gets rid of everything on this side except for 2 times square root of 2x plus 7. And that equals x minus 2x is negative x. And 15 minus 8 is positive 7. So negative x plus 7. All right, now we can square both sides. And that will get rid of the second radical. All right, 2 squared is 4 times this thing squared, this radical squared is 2x plus 7. And on this side, we're going to FOIL this thing. So that will be x squared minus 14x, right? 2 times a times b, and 7 squared, so plus 49. Okay. Now we can distribute here. So 4 times 2x, that gives us 8x, and 4 times 27 is 28. So 8x plus 28 there. Now we get everything over to the right. Subtract 8x. Subtract 28. That gives us 0 equals x squared minus 22x plus 21. Now factoring this, we're going to do x minus 21 and x minus 1. Setting these to 0 individually, we got 0 equals x minus 21 and 0 equals x minus 1. Solving these, we get x equals 21 and x equals 1. Alright, go back to the original equation. We're going to plug in 21. 2 times 21 is 42, plus 7 is 49. Square root of 49 is 7, plus 1 is 8. So we get an 8 on this side. And then over here, 21 plus 15 is 36. Square root of 36 is 6. So that does not work. No 21. Extraneous solution. Now let's plug in 1. Take 1, plug it in here. 2 plus 7 is 9. Square root of 9 is 3. 3 plus 1 is 4. Over here, 1 plus 15 is 16. Square root of 16 is 4. So 1 works. X equals 1 is the only solution. All right, now we're going to look at some applications of radical equations. And the first one, Valery Rozov holds the world record for the highest base jump. That's when you're standing on a cliff with a parachute, jump off, and then parachute. Very dangerous. Using the equation v equals square root of 64d, where v is the velocity and d is the distance that Valery has fallen. Determine how far Valery fell before reaching a speed of 300 feet per second, which is about 1 football field per second. So really cruising. Our equation is v equals square root of 64d. Now we have to figure out where to plug in the given value. All right? We're given a speed of 300 feet per second. So that goes in for v. So we get 300 here equals the square root of 64d. All right, now we can use the techniques we've learned so far to solve this one. So we're going to get rid of that radical by squaring both sides. So 300 squared so 90,900 there. There's 90,000. Yeah, that's right. So 90,000 equals, now we'll cancel the radical and the power, so we get 64d. Divide both sides by 64. And d equals 1,406 1/4 feet. So that's how far Valery had to fall before reaching a speed of 300 feet per second. It's quite a cliff. Our next example, Foucault's pendulum. It's a device used to prove the Earth's rotation. All right, so you get this pendulum swinging, and absent any forces on it, that pendulum is going to swing back and forth and not move. Back and forth. It's not changing its angle or anything like that. All right, so what Foucault did was then, as you can see in the diagram, put a bunch of posts around where the pendulum swings. Now, absent any forces, that pendulum should be going back and forth and hit one post on one side and one post on the other side, and just keep going back and forth and not hit any of the other posts. But what actually happens is that due to the rotation of the Earth, that pendulum is actually moving in relation to the posts. So it keeps knocking down posts one after the other, and that allowed Foucault to prove that the Earth rotated. Pretty ingenious. All right, the equation for the time of one swing is given by T equals 2 pi times square root of L over 32. Where T is the time in seconds and L is the length of the pendulum in feet. So we are given the time for one swing of the pendulum is 7 seconds. So we plug in 7 for T. All right, now we want to get this thing by itself, so I'm going to divide both sides by 2 pi. Get 7 over 2 pi equals square root of L over 32. And now we can get rid of the radical. And we get 49 over 4 pi squared equals L over 32. And then solving for L, we'll multiply both sides by 32. And that gives us L equals 49 times 32 over 4 pi squared. And if you plug that in the calculator, that's going to give us a length of 39.8 feet, so nearly a 40-foot pendulum to give you a period of 7 seconds. Now, we're back to the introduction. All right, we've got a ship, high mast with a lookout on the top. And they want to be able to see a castle that is 8 miles away. How far up above the ocean do they have to see? Do they have to be to see 8 miles away? All right, so what we have here is a very exaggerated curvature of the Earth here. And then you've got some boat out here. All right. And there's the crow's nest up at the top where the lookout sits. And they want to see some castle over here. And so if they're not high enough, they're just going to see ocean because the curvature of the Earth gets in the way. But if they get up high enough, then they'll be able to see the castle. So how high do they need to be? Well, let's see here. We got an equation D equals the square root of 1.5h. And D is the distance you can see, and h is the height above the ocean measured in feet. And D is the distance in miles. So we want to see 8 miles away, so we're going to plug in 8 here. We get the square root of 1.5h. And now we can square both sides. Now get rid of the radicals, so we get 64 equals 1.5h divided by 1.5 on both sides, and h equals 42.7 feet. So that crow's nest has to be 42.7 feet above the surface of the water. That is it for today, everybody.